Welcome back, guys. I'm Scott, and this is my second video in my two-part series about trigonometric ratios and the graphs of sine and cosine. If you watched my first video in this series, then you'll have already come up to this part where we have represented sine and cosine on the unit circle and put a triangle in there to understand how the triangle and the circle representations are the same and where these waves come from. If you haven't seen that yet, feel free to go back and watch it and then come back here so that we can talk more about these functions. So every time that we find some function in mathematics, the natural next step is transformations of that function. How can we move it around? How can we squish it? How can we change it a bit? And sine and cosine are no different. Today we're going to be focusing on the different transformations you can do on them. So if I go to a blank Desmos graph here, and I'll just put in our sine and cosine. Oh, they're blue and red right out of the box. That was nice of you, Desmos. Thanks. So the first thing that we can do to each of them, I'm going to look at just sine for now because most of what applies to sine will happen to cosine. And if I can add numbers here, so I can add 1 and see it moved up. I can make that 10 and see it moved all the way up to 10. And I can even make that a negative number, say -2. And now it's down here. So we have transformations that can happen by adding and subtracting different numbers. The other transformations that can happen to it is when we do multiplications at the front. So we can multiply this by 3, and it stretches upward. And we can multiply it by 0.5, and now it's kind of squished down. And all of these same things, will apply to cosine as well. So those are pretty straightforward once you think about them, Adding and subtracting numbers, that makes sense because, see, it moved up because you're adding 3 to every single point. So the points where it was 0 before on a regular sine, points where it was 0 here are now 3. And points where it was 1 are now 4. That makes enough sense. You're just adding a number to each so it'll move up and down, right? And then for multiplying at the front, that is also relatively straightforward. We multiply it by 3, and now the points where it was 0 are all still 0, because 0 times 3 is 0. And the points where it was 1 are all now 3. So everything's just been kind of stretched upward and scaled. And, same works for when you do small numbers. It's all kind of squished down because all the points where it was 1 are 0.5 now. So these are straightforward enough. But when it starts to get really weird is when we multiply the x on the inside. So when we multiply it by, say, 2 here. Oh, I should have kept that sign around. Silly me. See, now it's squished in. And now we are seeing a lot shorter cycles of our function. How exactly does that happen? If you watch the first video, you'll see that I gave a little preview where I changed on this graph, this little s variable, and made it higher. And you'll see it shrinks in, those graphs shrink in, and now it's moving faster. And then also I played with this big, attractive, shiny slider on my simulation. So let's play around with that a bit. You'll see down here in the corner, I have this speed variable. For all of the last video, that was kept at 1 because we were just talking about the shape of the graph. But now we want to talk about the speed. So if we take this slider and we turn it down a bit, see, suddenly our point is moving slower. Like I can turn it all the way down to 0 and see it's tracing out just a line because it's not moving. And I can make it just move slightly. Now it's just tracing out a very small slope. So if we take it down a bit from what it was, 0.8 instead of 1, you'll see that it's making kind of longer waves than it did before, but still the same general shape. And this should make sense, It's taking longer to go around, so the shapes that it make will be longer. They'll seem to be stretched out because it's taking more time for the point to move all the way around our circle. And then if we speed it up, you'll see that we have much shorter cycles. They're much sharper waves, and that makes sense as well, because it takes far less time for our point to move all the way around the circle. Now, that makes enough sense, right? But the only problem is, okay, we have our speed that we can change on the circle, but how does that tie into, 2x inside of there? How does increasing the speed relate to multiplying x inside of the sine function? In order to work with that, we're going to go to some pen and paper. So let's head over there. To answer this question, we're going to take a physics look at our point moving on the circle. In physics, things that are moving have velocity, right? Velocity being equal to distance over time. And this is often rewritten as distance being equal to velocity times time. This is going to be useful later. Then, we will often represent moving objects on the xy plane. We will have the x-axis be equal to time, and then the y-axis be equal to distance. We're going to change that up a bit here, though. When graphing sine and cosine, we will, instead of having distance on the y-axis, we will have the length of the line segment that represents the sine or cosine. To clear up what I mean by that, look at the triangle that we set up last time. We have cosine being equal to the x position of our point, and sine being equal to the y position of our point. And so when we're graphing cosine, we will look at that cosine line segment, and then when we're graphing sine, we'll look at that sine line segment and get graphs like this, like you see in Desmos, right? So when we're graphing it this way, because time is on the x-axis, when we're working with things algebraically, we will say that time is equal to x, right? And then the next variable we want to bring in is theta. Theta is just the distance that our point has moved around the circle in radians, right? That's theta right there. And because it's the distance around the circle, we're going to say that it's equal to our velocity of the point times time. So when we write sine of theta, we're really saying sine of our velocity times x, because x is the time that has passed so far. So with this look at things, as we change velocity, that will inside of our sine of vx, that will change how our point moves on the circle. So when velocity is just equal to 1, then that equals the graph of sine of x, like you usually put into Desmos. And then if we make it sine of 2x, that corresponds to making the velocity of our point on the circle be 2. So that is why we get more compressed and scrunched up graphs when we put in sine of 2x, because suddenly our point is moving a lot faster. So every time that you multiply x inside of a sine or cosine, then you're just making the circle turn faster because it's got to go fast. And that is our scrunching and stretching transformation. Now that we've looked at how multiplying the x inside of sine corresponds to squishing and stretching the graph and how that links into physics and velocity, we need to look at one last transformation. And this transformation is addition inside of our parentheses. So if we take x and add, say, 2 to it, suddenly it looks like our graph has kind of shifted over, right? If we made that 0 instead, see it's right here now, then add on 2, and now it looks like it's kind of shifted over that way. And if we were to make it negative 2 instead, see it looks like it's shifted over to the right. So the question that comes up is, why is this happening? Why is adding or subtracting from the x shifting to the left or right? In order to answer that, I went back into the simulation that I've been referring to this whole time, and I added some new features. So you can see there's this reset button, and there's this slider. So the reset just resets the simulation like you would expect. And then I'll take speed down to 0 so I can show you what this other slider does. But this slider changes the starting position. So if I slide it out here, you can see that now it started almost all the way up at the top, and it says distance turned is equal to 1.53. If I change it here instead, it's at a lower point. If I change it all the way here, it's almost all the way around that it's starting at. So this just changes the starting position. So if we go back to our graph here, I'm going to change that back to +2. Think about what x is. We've been talking about this whole time. Sine just takes in the distance we've turned around the circle. So the x here is the time that has taken place multiplied by our velocity. But when time is 0, velocity times time is just 0. We haven't moved anywhere. So whatever constant we're adding to that distance, whatever constant we're adding to x, is going to be our starting position. Where are we when time is equal to 0? So when we change our starting position here, that changes where we are when time is equal to 0. Now, it looks like it's moving left and right, right? When you just look at our graphs, it seems like they're shifting left and right when we add on constants, but that's not actually what's happening. You see, let's take it to, what's this value? 1.08, okay? Let's add 1.08 to, let's add 1.08 to this. You can see that on our simulation, it's higher than when sine usually starts. Instead of starting at 0 here, it's starting almost all the way up at 1. And then here, when time is equal to 0, usually sine starts at 0, but in this case, it's starting at 0.882, almost all the way up at 1. If we do another of these, we're going to turn it more so that it's kind of on the bottom. See, it's pretty much at 1 right there. Dang, that was lucky. It's starting at 4.68. If we make this 4.68, that's 14.68. We want 4.68. You can see it's starting at very nearly -1. Just like how this is starting at very nearly -1. So we change our starting point by adding or subtracting values, and that changes where our y-intercept is. That just shifts around our y-intercept, and in the process makes it look like it's moved left or right, but that's not what is really happening. So, over the course of today, we have looked at the different transformations of sine and cosine. We have seen how we can move them up and down with addition, and how we can stretch them with multiplication on the outside, and then how multiplication on the inside can compress or contract them, and addition and subtraction on the inside can move the y-intercept up and down as we change our starting position. If you have any confusion about any of these transformations at all, don't be afraid to just drop a comment and let me know what you're confused about, and I'll see if I can help you. See you guys next time.